Good afternoon, everybody. I hope that you're having a good week and that your day is going great so far. What we're looking at today is lesson 30.14, which is solving exponential equations. And we've already learned how to solve exponential equations by taking both sides of the equation and expressing them using the same base. However, what we're going to be doing today is looking at solving equations where that's not possible. And the reason why we're doing it now and not right after we looked at the other method was you have to use logarithms in order to solve these equations. The power rule with logarithms becomes very, very useful in today's lesson. So we've already learned how to solve exponential equations if we can write both sides using a common base. But if it's not possible, then we have to use logarithms to solve these. So we're going to go through 3 examples. Each of them are a little bit different, and they get progressively more difficult. And the third one is a beast of a question, but it's one that you definitely need to know how to do. First question is 4 raised to the x is 605. And no matter how hard you try, you will never find a common base here for both the left side and the right side. So what we're going to do instead is take the logarithm of both sides. And we're always going to, in this course, work with common logarithms, base 10 logarithms. So we will get log of 4 to the x equals log of 605. Now just a note to the people who were in calculus, you could certainly take the natural logarithm of both sides. But I'm going to stick with common logarithms in this course. Remember that the phrase common logarithm means base 10. So for example, log of 605 means log base 10 of 605. And we're choosing base 10 logarithms here, everybody, because we have a base 10 logarithm button on our calculator. Before we proceed, I want to point out to you that this question asks us to find the answer to the nearest tenth, but I also expect you to be able to find an exact value. So what we're going to do for all of our examples is calculate it in decimal form, but also express it as an exact value before we use the calculator. All right, getting back to the problem, we've taken the logarithm of both sides. How does this help us? It helps us because the power rule says the logarithm of a power is equal to the exponent times the logarithm of the base. So the logarithm, it's a base 10 logarithm, but it doesn't matter what base it is. The logarithm of 4 to the x is the same as x multiplied by the logarithm of 4. That's our power rule. Now the thing you need to understand is that log of 4 is a number. In other words, everybody, it is a coefficient of x. Well, if I had 5x equals a number, to get x by itself, I would divide by 5. So if I have x multiplied by log of 4 equals log of 605, then all I have to do is divide both sides by log of 4. So the exact value of x, everybody, is the logarithm of 605 divided by the logarithm of 4. This is an exact value. And you cannot simplify it. You can't divide 605 by 4. That wouldn't be allowed. If we want to know what the approximate decimal value is to the nearest tenth, then we can grab our calculator and take the logarithm of 605, close your brackets on that argument of 605, divided by the logarithm of 4, and we get an answer of, to the nearest decimal place, 4.6. That dot above the equal sign means approximate. So this is our decimal approximation. All right, we have 8 multiplied by 3 raised to the 2x equals 568. I would recommend dividing both sides by 8 to begin with. The 8's on the left cancel, and I'm left with 3 to the 2x equals 568 divided by 8. Something tells me that 8 does divide into 568 without remainder. 71. Now we can take the log of both sides. That allows me to move this exponent of 2x in front. Now I want to get x by itself. I'm going to rewrite this whole left-hand side a little bit different just to drive a point home. 2x log 3 means it's 2 multiplied by x multiplied by log of 3. Now, if I told you to figure out what 2 multiplied by 3 multiplied by 4 is, I hope you're able to get 24, but the point is I can multiply to get the 24. I can multiply 2 by 3 to get 6, and then multiply by 4 to get 24. I could instead multiply 3 by 4 to get 12, and then multiply that by 2 to get 24. Or I could multiply 2 by 4 to get 8, and then multiply that by 3 to get 24. The point is the order doesn't matter. So I'm going to choose to rearrange these in terms of how I write them as x multiplied by 2 multiplied by log 3. And then I can very clearly see that the coefficient of x on the left-hand side is 2 log 3. So that means, everyone, that if I take x multiplied by 2 log 3 equals log 71, and I divide both sides by 2 log 3, I will have x by itself. I'll have x equals log of 71 over 2 log 3. If I wanted to, I could write that as x equals log of 71 over log of 9. Because 2 log 3 is the same as log of 3 to the 2, and 3 to the 2 is 9. So either of these expressions here on the right are considered correct for exact values. If I want to know the decimal approximation, of course, then I can use my calculator. I'll just briefly here show you that if you take 2 log 3 and you take log of 71 divided by that, you get 1.94. And if I would have taken log of 71 divided by log of 9, I still get the 1.94. So the decimal approximation to the nearest tenth is 1.9. We have one more example left. This is the most involved example. It involves the most work. We're going to start off by taking the logarithm of both sides. And then we can move the exponents in front. When I move this exponent of 2x minus 1 in front, if I were to write this, that wouldn't be correct, because that looks like I'm saying 2x and then minus 1 log 4. What I need to do is put that exponent that I moved in front in brackets. Same thing on the right-hand side, x plus 2 in brackets multiplied by log of 3. Now, in order for us to get x by itself, you have to follow a very specific procedure. So you want to pay very careful attention to the steps that I outline here. The first thing that you need to do is take the logarithm and distribute it through multiplication into that binomial. And you have to do that on both sides. Always have to multiply things out. So what do I get? I get 2x log 4 minus 1 log 4. I don't think it's necessary to write the 1 there, but I did anyway. Equals x log 3 plus 2 log 3. That's the first step. Once you've moved the exponents down in front, you have to expand it out by multiplying. Your next step is to move any terms that have x to one side and the terms that do not have x to the other side. In other words, I want to make sure that this term and this term are on the same side of the equation, and that this term and this term are on the same side of the equation. Does it really matter which side you move things to? Not usually. In this particular case, if I move the x terms to the left, however, I will have fewer negatives. If I move the x terms to the left, I get 2x log 4 minus x log 3, and then I will have on the other side 2 log 3 plus log 4. So I moved this term to that side, and I moved this term to the other side. Let's review things, because there's one more step that's very important here. The first thing we did was we took the logarithm of both sides so that we could move the exponents in front. Then you multiply the exponents, which are binomials, by the logarithm to get a whole bunch of terms in your equation. Then you arrange it so that your terms with x are on one side, your terms without are on the other. Then your almost last step is to factor x out of the side of the equation that contains the x's. If I factor x out of 2x log 4, I'm left with 2 log 4. And if I factor x out of x log 3, I'm left with log 3. This is equal to 2 log 3 plus log 4. And now we're just about done. The only thing you need to recognize now is that to get x by itself, I can divide both sides of the equation by 2 log 4 minus log 3. And that will cancel with that beast in brackets on the left-hand side. So I divide both sides by the same thing. Which leaves me with x on the left, and on the right, 2 log 3 plus log 4 over 2 log 4 minus log 3. And by the way, again, if you wanted to, you could bring some of those coefficients up. I could move that 2 up as an exponent on 3 and have 3 squared. On the bottom, I could move that 2 up as an exponent on 4 and get 4 squared, which is 16. You don't have to do that. Either of these is correct. To get a decimal approximation, we're going to have to use our calculator. I would be very careful here, and I probably wouldn't recommend entering this into your calculator at once. I would probably calculate log of 16 minus log of 3. Make sure you notice how I close the brackets on each of those. And then in brackets, I would take log of 9 plus log of 4, and I would divide that whole thing by my answer. Either way, make sure you were able to get 2.14 or to the nearest decimal, 2.1. The assignment that you're going to be getting tomorrow will have a component to it where you are asked to solve an exponential equation similar to this one, and you're going to be expected to be able to come up with the exact values, which means you have to be able to come up with either this or that. Whether you go a little bit further on the assignment and find the decimal value would be entirely up to you. But you need to know how to do this type of problem for the next assignment. Tomorrow is a Google Meet day. In the meantime, you have some questions from your textbook that you can be working on page 413, number 2 and number 7. If you have any questions, feel free to send me an email before tomorrow. If you have questions tomorrow, show up to the Google Meet. And if I don't talk to you before the end of the day tomorrow, have a fantastic weekend. Remember, there's nothing going on Friday. And in the meantime, have a wonderful rest of the day, you guys. I will speak with you soon. Take care of yourselves.